So in this screencast, we are going to talk about another type of biomolecule and its application in cosmetics. This biomolecule is, or class of biomolecules that we're going to talk about are carbohydrates. These are a major source of energy. We get them mostly from our diet, right? They're made of the elements carbon, hydrogen, and oxygen. They're also called saccharides, which just means sugars, right? And these can range anything from what we would consider simple sugars like glucose, fructose, and sucrose to more complex sugars that you may have seen on food labels, for example. And those would be like starches and things of that nature. So some important things that these do just for our body is they provide energy through oxidation reactions and supply carbon for the synthesis of cell components. They also serve as a stored form of chemical energy, and they help form parts of the structural elements of some of cells and tissues. Now, there are four basic classifications of carbohydrates. These are monosaccharides, which are just the simplest carbohydrate. You can have disaccharides, which consist of two monosaccharides. Oh, you can have oligosaccharides, which are roughly 3 to 9 monosaccharides. We are not going to talk about oligosaccharides very much at all. The only reason I mention them is because they pop up a little bit in blood typing, right? So that's where blood types come from, is the oligosaccharides on the surface of the red blood cell. If you're more interested in that, please feel free to stop by my office. I can drone on for quite a while about how exciting that is, but that's really not what this course is focused on. So I mention it, but we're not going to go into detail. And then polysaccharides, which we contain many monosaccharides. We're going to say more than 10. Now I have some images here for you to look at. We have an example of a monosaccharide here with it's just one unit. Now, these are all carbons and hydrogens here. The thing that I really want to point out, though, is there is an oxygen in the ring. And so for this to be a carbohydrate, oxygen has to be included in the ring. So you can see an oxygen here and an oxygen there and a disaccharide. So these are linked through an ether bond, right? That's particularly called a glycosidic bond, and we're going to talk about that later. Notice here your polysaccharides have oxygens in the ring. Those are many monosaccharide units. So these are some examples of structures of carbohydrates. Now, carbohydrate structure can be shown as a ring like this, or it can also be shown as kind of this flat, straight structure. It's called a Fischer projection. When we talk about monosaccharides, there's a few things to notice. They're going to contain lots of alcohol functional groups. So we are going to have these alcohol functional groups, these hydroxyl groups, right, on the carbohydrate. They also can contain an aldehyde group. So we have the aldehyde group here. That aldehyde group, if the monosaccharide has an aldehyde group, it's called an aldose. Right? We also can see, right, that the other functional group that is present in carbohydrates are ketones. If the carbohydrate, the monosaccharide, has a ketone group, it's classified as a ketose. Okay, so we can have aldoses that have that aldehyde functional group, and then we can have ketoses, which has the ketone functional group. These have hydroxyl groups on all the carbons except the carbonyl carbon. So they have lots and lots and lots of these hydroxyl or alcohol functional groups. Now, we can also classify these monosaccharides by the number of carbons that are present. They're trioses if they have 3 carbon atoms. So what we do here is we use the aldo prefix because this has an aldehyde group here, right? So if there's an aldehyde group, we use the aldo prefix, right? If it's a ketone, if it contains a ketone group, we use the keto prefix, right? So when we look at these particular naming structures, we have a name here that's really specific for this molecule. It's its common name, but we have this larger classification name. It's got aldo here because we have the aldehyde functional group. It's got tri here because there's 1, 2, 3 carbons, and then it is it's a sugar, so it ends in OSE. So we would call this an aldotriose. When we have 4, the prefix there is tetro, so there's an aldehyde group. This is an aldotetrose. We have 1, 2, 3, 4, 5. This is a aldehyde group, so it'd be an aldopentose. There's 6 carbons here. That prefix is hex. There would be, and it's got a ketone group, so it's a ketohexose. There's one other that you run into really infrequently. If there's 7, we use the prefix hept. So 7 carbon atoms. It shows up one time in biological systems. So just in case you run into it and you're like, oh, we didn't talk about it. That's what you do see that every so often. So let's do an example, right? So it says classify each as an aldo or ketose and then as a tetrose, pentose, or hexose. If you want to try this on your own, this is great practice. My suggestion would be to pause the screencast now, try these on your own, and then restart, and we can go over the problems together. So when we look at this, the first thing we need to do is figure out if it's an aldo or keto. I'm going to find the carbonyl group, right? And I recognize that's an aldehyde group. So that's my first step, is to say, hey, look, that sucker there is an aldo because it has that aldehyde functional group. The next step is I'm going to count my carbons. 1, 2, 3, 4, 5, 6. There are 6 carbons there. I know that prefix is hex, and that ends in ose. So that is an aldohexose. We're going to come over here. We are going to look for our carbonyl functional group, or whatever functional group has that carbonyl carbon. We see it's in between 2 other carbons, so we classify that as a ketone. So that is a keto. And then we're going to count our carbons. 1, 2, 3, 4, 5. There are 5 carbons here, so the prefix there is pent, and then ose. All right, I always want to count, when I count carbons, I always want to count like the count from Sesame Street. But I just want you all to appreciate that I avoided doing that on the screencast. But do not worry, I probably will do it in class. Now, let's talk a little bit more about some of the structural elements of our monosaccharides. When they're shown in the straight chains like we've been looking at, they're called Fischer projections. When they're shown like this, it places the aldehyde group or the ketone group, the most oxidized group, at the top, okay? And what happens is, what you do when these are organized this way is you're going to have your ketone group closest to the top and then your CH2OH group closest to the bottom. When we do this, what you're going to see in some of our naming is you're going to see an L and a D. This just is the reference for, on the very last carbon next to the CH2OH, where is this OH? If the OH is on the left side, it's called L-glyceride. If the OH is on the right side, right, that's where we get that D prefix. Now, you're going to see this pretty frequently because most sugars in nature are in the D configuration. And so that's what you'll see most often. But so if you see the L or the D on a sugar, that's what it's talking about, is the placement of that very last carbon and whether the OH is on the left or the right side. Now, we see these linear structures, these Fischer projections, pretty frequently, but more often as we go through, particularly some important monosaccharides and disaccharides, and polysaccharides, you are going to see the ring form as well. Ring form a lot of times is referred to as a Hayworth structure, right? That's the ring structure. So if you see Hayworth, that's what it's talking about. And basically, you are not going to have to do this, but I want you to be able to recognize it. Okay, so don't panic on me here. But if we take, this is D-glucose. Okay, it's a aldohexose. We've got the carbons numbered here. If we take that and flop it on its side, we're just going to turn it clockwise by 90 degrees, right? Here is that number one carbon with the aldehyde group. Then, right, if we look at this and take, so we've got these carbons here, 1 through 6, and we take and we kind of fold that molecule around where now here are our carbons 1 through 6. What happens is this OH on carbon number 5 reacts with the carbonyl carbon. There's a couple reasons this happens. It's really outside the scope of the course. I'd be more than happy to tell you more details about it if you want to stop by my office. But it will attack right here. Okay, and that's how we get the oxygen in the ring that's so critical for recognizing when things are carbohydrates. Okay, now when it does this, in this ring structure, the OH and the hydrogen that were on that first carbon, so the carbonyl now becomes an OH, an alcohol group. It is rigid. It's stuck either above or below the ring. Okay, so this dark line, imagine it's coming out. This is flat. This is above the ring. This is below the ring. If it is above the ring, right, we call that beta. So if it's above the ring, it is beta. Okay. If it is below the ring, right, it is alpha. Okay. The way that I remember this is a vowel and that's a consonant, and this is a vowel and alpha. Sorry, this is a consonant. Beta is a consonant. B is a consonant, and alpha is a vowel. And when you're thinking about above and beta and below and alpha, the two vowels never go together, right? You always need to have a vowel and a consonant, and that's how I remember it. And so you're going to see some references of beta and alpha as we go through, and that's where that comes from. Now, let's talk about some important monosaccharides that we run into. One of the important monosaccharides that we run into that pops up quite frequently in nucleic acids, which are like RNA and DNA, are ribose. So you can have ribose. This is just the normal structure of ribose. You can also have deoxyribose. This D prefix just means it's lacking, right? And if it's the oxy, it's lacking in oxygen. And that's lacking in oxygen in the number 2 position. So see this number 2 carbon here? It's missing a hydroxyl group, an OH. And that's where we get the 2-deoxyribose nucleic acid from. Okay? So ribose just forms the long chains that make up RNA. Right? So that if you see D-ribose, that's an RNA. Deoxyribose forms the long chains of DNA. And these, of course, are our sugars. You can see, I've got them in the Fisher projection. You can also see them in the Hayworth projection, right? And you can see that OH that's missing in the number 2 position between the beta D-ribose and the beta deoxyribose. Glucose is the next monosaccharide we're going to talk about. It is the most nutritionally important monosaccharide. It's a lot of times called dextrose, right? Or blood sugar, or grape sugar because it was discovered in grapes, right? All of these are that beta D glucose. This is the final form that all the sugars in your body are converted to. It's also used as a sweetener in foods, right? And so you can see it quite often as foods. It's an aldohexose that's shown right there. Our next monosaccharide is galactose. Galactose is a hexose with a similar structure to glucose. The big difference here is in the 4 position. The OH is up in galactose where it's down in glucose. So it's just that location of the OH. This is one of the components of the disaccharide lactose, right, which is a milk sugar. So galactose is one component of lactose that we'll run into. Fructose is the sweetest monosaccharide. A lot of times it's called levulose or fruit sugar. It's present in honey in a 1-to-1 ratio of glucose. So that's where its big prevalence is. You can see my picture of honey here and the D-fructose here. It's also very abundant in corn syrup. That's why it's a lot of times called high fructose corn syrup, is because it has this particular sugar. It forms a 5-membered ring because of this ketone group here when it's in its Hayworth projection. So it looks a little different, but that's what happens when there's that ketone in the 5th position instead of the 6th position with the aldehyde. Then you get a 5-membered ring here. Let's talk about disaccharides. Now, disaccharides are when you have 2 monosaccharides that are linked together by a glycosidic linkage. Now, this is a lot of times called an acetyl or a ketal glycosidic linkage. You don't have to worry about that, but I like to put it in there in case you run into it. These are identified 2 ways. So when we look at alpha D-glucose here, and we have that carbon numbering system where we identify number 1. So in this carbon numbering system, the number 1 carbon is the one that's bonded to 2 oxygen atoms. It's the only one, right? There's only one of them. It's only 1 carbon that's bonded to 2 oxygen atoms. So we come here to 2, 3, 4, 5, and 6. And so that's what we see as far as our numbering is concerned. Same thing over here. 1, 2, 3, 4, 5, 6. When these bond and we describe the bond that forms, you are going to notice that there are numbers here, 1 to 4, that are saying, hey, look, we're linking the number 1 carbon in one monosaccharide to the number 4 carbon in another monosaccharide. When we do this, that's our 1,4 glycosidic linkage. Sometimes you will see this in some older text as 1,4, okay, as the glycosidic linkage. Now, where do we get this alpha from? That comes from the configuration of the anomeric carbon. The anomeric carbon is the one that's attached to 2 oxygen atoms. That's the name for that carbon. So when I look at this, right, this guy here is the one that's attached to 2 oxygen atoms. So is this guy here. But look, this one is the only one that's involved in the bond. That's where the alpha comes from. That OH group is right down. So it's an alpha, right? We also see alpha D-glucose there. And so that is where the alpha comes in naming these linkages. And that's important because sometimes, like particularly if we're eating these, our bodies can only digest certain ways that these bonds are, either alpha or beta. All right, let's talk about some important disaccharides. Maltose is one that we will run into. It's called malt sugar. It contains 2 glucose units that are joined by an alpha 1,4 glycosidic linkage. It's generally found in germinating grains, so it pops up in things like beer, and it's formed during that digestion of starch to glucose. Lactose is another disaccharide we run into pretty frequently. It's a lot of times called a milk sugar. It is made of a galactose unit and a glucose unit. So you've got beta 1,4 glycosidic bond here that links these 2 together. If you are lactose intolerant, it means that your body you do not have the enzyme that can break this linkage here. And so that's what causes there to be an upset stomach, if that's something that you run into. Our next disaccharide that we're going to talk about is sucrose. Sucrose is just known as common household sugar. It's the structure is kind of wickety wild. When we look at this, we've got two anomeric carbons that are linked. This one is in the alpha configuration. This one is in the beta configuration. So we have to tell if they're alpha or beta for both of those. So we see alpha, comma, beta, and then 1 and 2 for those carbons. And that's kind of the structure that we see there. When we look at this, it's a glucose unit and a fructose unit. So that's what it is made out of. It is found in plants like sugarcane and sugar beets, and that's where we get that cane sugars from sugarcane. If sugar doesn't say it's cane sugar, it's coming from beets. It's still sugar. It's still fine. It's just beet sugar doesn't quite have the ring that cane sugar does. Now, where do we see this in cosmetics? A lot of times it's used in sugar scrubs, right? So if you are using a sugar scrub for exfoliation, you've got sucrose in there probably. It's also a lot of times used as a sweetening or a flavoring agent because it's sweet. In things like lip balms, right? So if you've ever put on a lip balm and it's kind of sweet, it probably has a little bit of sucrose in there. It also absorbs water. So a lot of times people refer to this as like a humectant, right? One of the things that's going to help absorb water onto your skin. So let's talk about polysaccharides. Polysaccharides, right, have more than 10 monosaccharide units that are linked, right? That's what we see. These consist of, so the first one we're going to talk about is starch. Starch is found in like your starchy foods like potatoes or pasta or things like that. It consists of D-glucose units. There are two components of starch. You have amylose and amylopectin. When we look at amylose versus amylopectin, basically amylose is unbranched. It's gonna do this really nice linear structure that kind of has these units that turn into a helix, right? It's gonna wrap there. Then we also have amylopectin, and amylopectin is branched, right? And so when we talk about starch, it's a combination of two of these, where amylose makes up about 10 to 20% of starch, whereas amylopectin makes up about 80 to 90% of starch. Now, the branching occurs because we have some alpha-1,6 glycosidic bonds, and that's why we get that branching. Now, starch is found in cosmetics in a few different places. It's used as a thickener, binder, and absorbent, right? And an absorbent just reduces shininess in your cosmetics. So you find starch a lot of times in things like face powders, right? Or blush. So those powdery things. It's used pretty frequently in dry shampoo to help kind of bind the oil and dry that up. And every so often you can find it in things like creams and lotions. Right? So that's where we're going to see starch be used in cosmetics. Glycogen is another polysaccharide. This a lot of times is called animal starch. It's how our body stores carbohydrates, right? Particularly in the liver and the muscles. It's structurally similar to amylopectin with the alpha-1,4 and alpha-1,6 linkages. It's just more highly branched. This has started to show up in some cosmetics because it's very hydrating, right? And it can reduce fine lines and wrinkles. So a lot of times it's used as a humectant, right? And all that means is it's going to attract and bind water. I've found it. So I just did a search because I was not particularly familiar with glycogen being used in cosmetics. And one of the things that turned up was this particular eye cream. It's a vitamin C eye cream. It's a Q&A eye cream, a blend of cherry extract and glycogen to reinvigorate delicate skin, delivering an essential hit of moisture. So you're starting to see some of the glycogen show up in cosmetics, and so I'm assuming they can be listed in the glycogen would be listed in the ingredients as well. This is just a product that I found on Amazon that I thought was a really good example of glycogen being advertised to help reduce wrinkles or reinvigorate skin, those types of things. Basically, it's being used as a moisturizer. Other carbohydrates that we find in cosmetics are things like that you'll see are like hyaluronic acid and sodium hyaluronate. You can see there's a serum here that I found online, a picture of. When we talk about that hyaluronic acid, this is the polymer structure. So when you see a polymer structure and you see these brackets right here with an N, all that means is this group, these two groups that are linked, are repeating over and over and over again. Now, we have this hyaluronic acid. It can also form a salt, and when it does that, it's called sodium hyaluronate. And you can see both of these on labels. When we talk about this, the type, this is called a glycosamino glycan, right? And so when we talk about amino, right, that indicates to us that we're going to have a nitrogen. And what we actually have is an amide bond right here. So that's unusual in the carbohydrates that we talked about, right? At the beginning, I said, hey, look, it's going to be carbon, oxygen, and hydrogen, right? But it turns out that if there is this amide functional group or an amine, a lot of times it's classified as a glyco, which is what tells us it's a carbohydrate, aminoglycan. So that's what it's classified as. That's a type of polysaccharide. The function here is this is a humectant. It's actually quite a good humectant. It can hold up to 1,000 times its weight in water, right? And so it's super great for moisturizing, right? And this idea that you're going to plump your skin. And if you plump your skin, you're going to reduce the appearance of those fine lines and wrinkles. It also kind of touts this idea that it's going to improve your skin elasticity. The reason people may use this is it's just more stable than that acid form, right? So that may be why it's used more often. This is found in serums, like I'm showing you here, moisturizers, eye creams, and anti-aging products, right? It's also used in skin injections in the face to reduce wrinkles. So you can see it being used in some skin injections there. Another polysaccharide that is found in cosmetics is carrageenan. This is found in cosmetics, and it is also found in a lot of foods, right? So you will see this as an additive to your food because it is a thickening agent. So this is a polysaccharide. It's a sulfated polysaccharide. because it has this sulfate group here, and the sulfate group here, and the sulfate group here. Okay, so it's got 3 sulfate groups. This is the structure that repeats for the polysaccharide. It is derived from red seaweed, which I have a picture of here. So that's where we get the carrageenan from. It is a gelling, thickening, and stabilizing agent. I worked with a biologist who would not eat anything with carrageenan in it. He said it left a kind of a funny texture in his mouth that he didn't like, and so he would hunt around for things that didn't have carrageenan in them. I have never noticed that. That was just something that he talked about quite a bit. Basically, what this does is it provides a smooth feel for your cosmetics, and it also has some hydrating properties. It's a film former, so it'll form a film on the skin. It's found in things like lotion, creams, shampoos, anything that you're trying to make thicker, conditioners, shower gels, facial masks. Right? So found in quite a few places. Our next polysaccharide we see is cellulose and its derivatives, right? So hydroxyethyl cellulose, carboxymethyl cellulose. These are just groups that are attached to the cellulose gum. Cellulose itself is a really important structural polysaccharide. It's the most abundant on Earth. So this is the most abundant polysaccharide on Earth. Okay. Because it comes from, it's the material of plant cell walls. So it's the material of plant cell walls. Like amylose, this is a linear polymer consisting of D-glucose units joined by an alpha-1,4 linkage. So this is just a polysaccharide that's derived from plants. Its function is that it's used for a thickening agent. It's also used as a binder and an emulsion stabilizer. It really can create a gel, help create this gel-like consistency, and it helps improve product spreadability. It also prevents ingredients from separating. Some of them can help form films, right? So it's found in things like shampoo, conditioner, lotion, creams, and toothpaste, right? So it pops up quite frequently. Our next polysaccharide is xanthan gum, right? This is a polysaccharide produced from bacterial, or by, probably would be better, fermentation. You can buy it in a lot of different places. It's also used in food. So for example, I searched xanthan gum because I wanted to show you, some things where you could see it. And Bob's Red Mill popped up here, great for baking, right? It's also used pretty heavily in cosmetics. It is a thickening agent and emulsion stabilizer, right? And you can see the structure of it here, right? So there's the structure. It is found in almost all types of liquid and semi-liquid cosmetics products. So it's in serums, right? Creams, cleansers, and foundations. Our next polysaccharide is beta-glucan. This is a polysaccharide that's derived from oats, mushrooms, or yeast. So those are the places that it comes from. You can see this in a skincare product. Here is the repeating polysaccharide units. It's known for kind of this idea that it's hydrating, right? And it's skin protective. So people say a lot of times it can help calm, right, irritated skin, right? So that's the claim. Probably because it helps support the skin barrier. It's found in serums, moisturizers, and soothing creams. Right? The next polysaccharide that we see are alginates. Alginates, which when we look at this, you're going to see a couple names for this. A lot of times this is called alginic acid, right? It's also known as algin, right? It's just a naturally occurring polysaccharide that's found in brown algae. So it's a polysaccharide from brown seaweed, basically, right? It's really hydrophilic and it forms a really thick gum when it's hydrated. Now, when it binds to sodium and calcium ions, it forms a salt. So this is when the polysaccharide binds to sodium or calcium ions, right? That's when it's called an alginate. And so sometimes that's a little bit more stable, and so that's what people buy. So it's really valuable. So its function here is it forms a hydrating and protective skin, protective film on skin. And so it is found in things like masks, moisturizers, and body lotions. I got thrown off because there was knocking at the door. So I also wanted to point out here, it was thickening. It's a thickening and gelling agent. I was looking for like products that had this in it and ran upon a site that sells cosmetic things to make cosmetics, right? And so I thought this was a really nice image to show it being used in a mask. If you're more interested in that, you can go to the website, and that's where that's from. Finally, our last polysaccharide here is dextrin. This is a polysaccharide produced by bacteria. Its function is it's a texture enhancer, right? So it's a thickener, it's a stabilizer, and a hydrating agent. Let me put down thickener there too. So because of this, it's found in just a variety of products, a lot of skincare products like lotions, a lot of hair products like shampoo and conditioner, mascara, right? Brow liners, right? Concealers, foundation, all of these particular products. So I found a scalp serum because I wanted to see, I wanted to show you where it was in there. And so you can see there's dextrin right there. as part of the ingredients. I also want you to point out there's xanthan gum right there that we've talked about before as well. You can probably look through this and find a few other ingredients that we've talked about, either when we talked about our functional groups, like the phenoxyethanol, or as we've talked about, our fats and our carbohydrates. The next screencast, we are going to talk about peptides and proteins and how those are used in cosmetics. As always, if you have any questions, please feel free to pop by my office.